Geometry students, welcome back to your 10.5 notes on tangent lines of a circle. And we are going to continue with our notes from the other day that we kind of had to leave off because we didn't finish them in class. And so today we're going to finish those up. Here we go. We have two tangent lines that start at the same point R right here. Okay, and so if two segments from the same point exterior to the circle are tangent, then they are congruent. So if this line segment RQ starts at the same point R, and then the line segment RS starts at the same point R, and they are both tangent, then we have two congruent lines. And so we've already indicated that here, and we've set up our problem. So let's go ahead and solve for x. We can subtract 8 on both sides using the subtraction property of equality. And we would get 3x is equal to, let's see, that would be 18. I can divide both sides by 3, and I would get x is equal to 6. Okay, so moving on to number 2, if I've got two line segments that begin at the same point exterior to the circle, and I've got two tangent lines, and it says that I can go ahead and assume that the lines that appear to be tangent are in fact tangent. So then that means that I could say that segment WX is congruent to segment YX, and I could say that 2x plus 9 is equal to 3x plus 6. 3x plus 6. And then I would go ahead and solve for x. I can subtract 6 on each side using the subtraction property of equality. I can subtract 2x on each side using the subtraction property of equality, and I would get 3 is equal to x, and that would solve for x. All right, so in example number 5, we have a circumscribed polygon, and it basically says quadrilateral RSTU is circumscribed about circle J. If the perimeter is 18 units, find x. So what we have going on here is a couple of tangent lines that are similar to the situations that we were experiencing up here above, where we've got two tangents from the same point exterior to the circle. All right, so we've got a tangent TB, and we've got a tangent TA, we've got a tangent UC, and we've got a tangent UB, we've got a tangent SA, and we've got a tangent SD, we've got a tangent RC, and we've got a tangent RD. And so we've got all these many tangents here. Basically what that means is that this line segment is congruent to this line segment, this line segment is congruent to this line segment. In this particular case, they happen to be those line segments happen to be congruent. If they weren't, we could use a different hash mark, but since they are actually congruent, we can go ahead and indicate that. And we've got a line segment SA that is congruent to SD, and same thing with RC and RD. So if we know that the perimeter is 18 units, we can go ahead and set up an algebraic situation. All right, if this line segment TB is equivalent or congruent to line segment TA, I can say that that's equal to x. Same thing with BU, and same I can say with RC. It's congruent to RD, so I could say that this line segment is 3, and I can say that this line segment is 3SD. So what we could say is that since we know that the quadrilateral has got a perimeter of 18 units, and to calculate the perimeter, all I need to do is add everything up. So I would have, let's see, 1, 2, 3, 4 x's. All right, I've got 1, 2, 3, 4 3's. All right, so if I solve that, I can find out what x is going to be. So I've got 18 is equal to 4x plus 12. I can use the subtraction property of equality and subtract 12 on both sides of my equation, and I would end up with 6 is equal to 4x. And then I could divide both sides by 4, and I would get x is equal to let's see, both of those are divisible by 2, so I'm going to call it 3/2. And I'm going to leave it in fraction form. You could call that 1.5, but I prefer the fraction form. Alright, I have one more example here for you. What I would like you to do is go ahead and pause your video and draw this triangle JKL, which is circumscribed about circle R. Go ahead and take a second, pause your video, and draw a sketch of that scenario. Okay, I hope that you went ahead and paused your video and drew a sketch of the triangle JKL, and it is circumscribed about circle R. So we've got another similar situation to what we've been discussing, where we've got these little tangents that occur from a point outside of the circle, exterior to the circle. So we've got line segment LN is congruent to line segment LO. We've got line segment KN is congruent to line segment KM. And we've got line segment JM is congruent to line segment JO. Alright, so first it asks us to find X. Alright, and I can go ahead and set 4x minus 9 equal to x plus 3 in order to find X. I can also go ahead and just set that side equal to 7 and this side length or this segment equal to 12 and this segment equal to 7. Okay, so first it told us to find X, so I'm going to go ahead and solve for X. I'm going to go ahead and let's move this X over here using the subtraction property of equality, so I'll have 3x. I can add 9 to both sides using the addition property of equality, and I would have 3x is equal to 12. If I use the division property of equality, I would have x is equal to 4. In order to find these lengths over here, I could substitute 4 for x, so I would get 4 plus 3 would be equal to 7. And I would get 4 times 4 minus 9 is equal to, that'd be 16 minus 9, so that would be equal to 7. Alright, so these two side lengths are equal to 7. Alright, so that would make line segment KL equal to, let's see, that would be 7 plus 7, so that would be 14. We could say that line segment JL would be 12 plus 7, so JL would be 19. We could say that JK would be 19 as well. JK would be 19 as well, because you would have 12 plus 7 there. So the perimeter, I could add up all three of those lengths, and I would get my perimeter. So the perimeter of triangle JKL is 52. That concludes your 10.5 notes. I do have an assignment for you today for you to work on while the substitute is there. And I hope that you enjoyed the video. We will see you soon in class.